Welcome to the Explainer. Today, we're going to pull back the curtain on something, a hidden system that pretty much makes our entire modern world possible, and that is calibration.
I mean, really, think about it for a second. When you fill up your car with gas, or you glance at your speedometer, or heck, even when you step on the scale in the morning, you're just trusting a number. But how do you know that number is actually right? How can you be sure that a thermometer reading 98.6 degrees isn't really off by a few points? Well, all of that trust, it's all built on the science of calibration.
Okay, so let's dive right in. The word calibration gets thrown around a lot, right? But in the world of measurement, what does it actually mean? Turns out, it's something very, very specific and incredibly important.
You know, at its core, calibration is surprisingly simple. It is purely an act of comparison. That's it. You take the thing you want to check, what the pros call the device under test, and you compare its reading to something called a calibration standard. That's just an object or an instrument that you already know is super accurate. You're basically just asking a simple question. Does my ruler match the master ruler?
And this right here, this is a huge point that trips a lot of people up. Calibration is not the act of fixing something. That's a totally different thing called adjustment. See, first you calibrate just to find out if there's an error, and if so, how big that error is. Then, and only then, might you go in and perform an adjustment to fix it. They are two totally separate steps, a really important distinction. So, okay, it's just a simple comparison. Big deal, right? Well, yeah, it's a huge deal, because without it, honestly, so much of our technological world would just grind to a halt. It's this invisible system of trust that's running in the background all the time.
I mean, just look at all the places this matters. A caliper, making sure a machine part is made to the exact specification. A scale at the grocery store, making sure you get exactly what you paid for. The measurements in a science lab, absolutely critical for research. And that pressure gauge? That could be part of a safety system on an airplane or in a power plant. It's this hidden network that guarantees quality, fairness, and, safety.
And believe it or not, this is not a new problem. Not by a long shot. For as long as people have been building things and trading with each other, we've needed standards. He had King Henry I trying to make the yard the distance from his nose to his thumb. Not exactly scientific, right? The Magna Carta, way back in 1225, tried to standardize measurements for wine and ale. And then, bam, the Industrial Revolution hits, and you get these complex new gauges that had to be calibrated against something more basic just to be useful. The challenge has always been the same. How do we all agree on what's correct?
So that leads to a pretty obvious question, doesn't it? If you're calibrating your device against a standard, well, what was that standard calibrated against? How do you know the thing you're using as your source of truth is actually true?
The answer is this really powerful idea called metrological traceability. And the best way to think about it is, well, exactly like this, an unbroken chain. Every single link in that chain is a documented calibration, connecting your measurement all the way back, step by step, to a single authoritative source.
So here's the official fancy definition from NIST. That's the National Institute of Standards and Technology. The key phrases you want to grab onto here are documented, unbroken chain of calibrations, we just talked about that, and this other idea that each link contributes to the measurement uncertainty. Now hang on to that second part. We're going to circle back to it in just a minute.
Okay, this visual just illustrates it perfectly. Let's take mass, for example. Way down at the bottom, you've got your field standards. Think of the weights used to check the scale at your local deli. Well, those weights get calibrated by a lab that uses even more accurate standards. And those lab standards, they were compared against even better primary standards, which, you guessed it, ultimately trace their calibration all the way back to the national standard. It's like a pyramid, with each level getting more and more accurate as you go up.
And it's not just for weight either. The exact same idea applies to, say, length. That 100-foot tape measure a surveyor uses to lay out a new building? It gets its accuracy from the very same kind of unbroken chain, connecting it all the way back to the national standard for the meter.
Okay, so this chain gives us trust. It gives us confidence. But what it doesn't give us is perfection. Because, and this is important, no measurement is ever truly perfect. And the science of measurement, metrology, doesn't try to hide that fact. In fact, it embraces it. It quantifies it with a concept called uncertainty.
So, just like we separated calibration and adjustment, we need to separate error from uncertainty. They are not the same thing. An error is a flat-out mistake. If your scale is always 2 pounds heavy, that's an error. You can fix it. But uncertainty, that's different. It's more like a quantified doubt. It's a way of stating the small range around your measurement where the true value could reasonably be. It's like saying, the measurement is 10.01 inches, give or take a tiny fraction of an inch.
And where does this doubt, this uncertainty come from? Well, everywhere. It could be tiny changes in temperature or humidity in the room. It could be the person reading the dial just not seeing it perfectly straight on. Even the instrument itself has physical limits on how precise it can be. All these little things add up and contribute to the total measurement uncertainty.
And this quote from NIST really just ties a perfect bow on it. Having a traceable measurement gives you confidence, for sure, but it doesn't magically make uncertainty disappear, and it certainly doesn't mean you can't make a mistake. All traceability does is prove your measurement is linked to the official standard. The uncertainty statement is what tells you just how good that measurement actually is.
So let's zoom out and put this all together. You've got calibration, this active comparison, you've got traceability, this chain of trust, and you've got uncertainty, this honest admission of doubt. The combination of all three creates this incredible global system that allows us to build and trade and innovate with a huge amount of confidence.
So the actual process from start to finish kind of looks like this. It all starts with designing an instrument that's stable enough to hold its calibration. Then you define the exact process, you do the comparison in a controlled environment, you document everything, especially that uncertainty number, and you make sure the standard you're using is itself traceable all the way up the chain.
And here's a cool little insider detail, a rule of thumb in the industry. For a calibration to be considered really valid, the standard you're using should be at least 4 times more accurate than the thing you're testing. This 4-to-1 ratio pretty much guarantees that any tiny uncertainty from your standard is so small it barely affects the final result.
All right, so if you're going to take away just 3 key ideas from all of this, let it be these. 1. Calibration is simply the act of comparison. 2. Traceability is that unbreakable chain of trust. And 3. Uncertainty isn't an error, it's a quantified doubt. It's an honest part of the process. It's this invisible infrastructure, right? This global agreement on standards that just lets our complex world work. It's always humming along quietly in the background, making sure our measurements are meaningful and reliable. Which kind of leaves us with one last question to chew on. What uncalibrated measurements are you trusting today?